protect your wealth by spending physical gold, not paper money that grows weaker by the second, on a...
When people do a study of, for example, the double slit experiment, and they approach the double slit experiment in the traditional way, one particle at a time, a wave function that we can pretend is moving in three-dimensional space, but this is really just an artifact of the fact that configuration space for one particle looks three-dimensional. It looks like you should treat the particle as a wave as it goes through the slits to get the correct pattern over many repetitions of landing sites. We don't actually see a wave on the other side. What we see is dots, many, many landing sites over many repetitions of the experiment. The wave is inferred. But when you measure where the particle is at the end of the experiment, or you measure which hole it goes through, you get a particle duality. This is further complicated by the fact that there are waves of a different kind in physics. Electromagnetic waves, for example. Light is a disturbance in the electromagnetic field that propagates like a wave through three-dimensional space. And those are waves. I mean, like I said, I teach Jackson electromagnetism. We talk about waves moving through three-dimensional space. It's very easy to confuse the waves of a field, like the electromagnetic field, with the wave functions or Schrödinger waves of quantum mechanics, but they're not the same thing. And this has bled into the wave-particle duality. When Planck in 1900 and Einstein in 1905 and various people were proposing that light came in quanta, discrete particle-like quanta called photons, the wave that they were imagining was the wave corresponding to photons was a three-dimensional electromagnetic wave, a wave of the familiar kind of wave. The wave functions that Schrödinger introduced in 1926 were not like those waves. They were not three-dimensional waves in physical space of a field. They were these abstract, complex valued functions in a high-dimensional configuration space. And when you measured them, they collapsed. Now, if you're in an MRI machine and they've turned on a very strong magnetic field, you don't have to worry that if you do the wrong measurement, you're going to collapse the magnetic field in the MRI machine. It's not that kind of field. The waves they're beaming at you are not those kinds of waves. So you have the waves of a field and Schrödinger waves. And I want to make super clear that in the indivisible stochastic approach to quantum mechanics that we've been talking about, I'm saying Schrödinger waves are not real things. These abstract things that live in this high-dimensional configuration space, those are not physically real. But classical waves, or the waves of a field, which are a different, conceptually different kind of a wave, those are perfectly valid. And if you're studying a system that's not made of particles, but a system made of fields, you're going to see wave-like behavior as well. But those are a different kind of wave. And these are the kinds of subtleties that I think get lost when someone just says wave-particle duality. So again, just to summarize, the relationship between a photon, a particle of light, and an electromagnetic wave is not like the relationship between an electron and a Schrödinger wave function for the electron. Now, what makes this even more confusing is that electrons do have fields also. There's a so-called Dirac field that plays a very important role in the Standard Model. And this is a field in three dimensions for the electron. But the Dirac field for the electron is not the Schrödinger wave for an electron.